Okay, guys, so this one is the the lesson for 3.9 calculus. Okay, so related rate. So anytime that you solve for the related rate problem, so that means you want to compute the rate of change of one quantity in terms of time. And for examples, such things that's like the rate of change of a distance, velocity, the rate of change of volume of an object, like dv over dt, and then the rate of change of area of any geometric figures. Okay, so, and those are the things considered related rate problem. So here are the strategy for solving related rate problem. Read the problem carefully and identifying all the quantity terms. Second thing that you want to do, you want to draw a diagram to describe the given problem. And then step 3, you want to set up a main equation and auxiliary equation. An auxiliary equation is like a second equation that you want to find out one variable in terms of the other variable. And then for step 4, you want to differentiate the main equation implicitly with the variable. And then step 5, you want to solve for the unknown quantity. So we'll find out some of the example in a minute. So here's one of those. So the length of a rectangle is increasing at the rate of 8 centimeter per second. And its width it's increasing at the rate of 3 centimeter per second. So one is the rate of change of the length, the other one is the rate of change of the width. And when the length is 25 centimeter and the width is 15 centimeter, how fast is the area of the rectangle increasing? So first thing that you want to do, you want to draw the rectangle. Okay, so let's see what I got here for the figure. Okay, it looks like I don't have the shape figure here as what I have at Kennedy for the Promethean board. So let's just draw it out. Okay, so let's say that we do have a. Okay, so set up the line segment here. So it's a rectangle. So another thing that we need to know is that the length and the width. Okay, so we do have a length here and the width right here. Okay, so we do know that the length of the width, they can be changing anytime according to the time. So that means we can find out dl over dt, which is the rate of change, and then dw over dt. So one thing that we noticed, the way to find the area of a rectangle is length times the width. So since we do have 1, 2, 3 variable, so that means we can take the derivative implicitly. So we do have dA over dt. And then for the length and the width, we need to use the product rule to take the derivative. So for the first one, we got dl over dt times w, and then plus derivative of w, dw over dt. Again, it's implicit differentiation times L. So now, according to the question, we want to find out the speed of the area, the rate of change of the area. So dl over dt. Well, another thing that we forgot to do here is about the annotation. So this one, the length increasing at the rate of 8 centimeter per second. So that one is dl over dt. And then dw over dt, then that'll be 3 centimeter per second. Okay, so you want to highlight the key information and then annotate. And then, now when the length is 25 centimeters and the width is 15 centimeter, so you want to find out the rate of change of the area. So now let's plug in a number. So dl over dt, which is what, 8. And then w, so w is 15. And then dw over dt, so dw over dt, we do have 3 centimeter per second. And then times L times 25. So now you want to find out exactly what dA over dt is. So 8 times 15, so 8 times 5 is 40. 1 times 8 plus 4, so it's 120. And then 3 times 25, 75. So it's 195. And then the unit, it's the area. Well, the rate of change of the area. So that means it's square centimeter per second. So this one, it shows how fast the area is being increasing. Okay? So now, let's check out the other example. So the radius of a sphere, it's increasing at the rate of 4 millimeter per second. And how fast is the volume increasing when the diameter is 100 millimeter? So this one is going back to geometry. The way to find the volume of a sphere. So the volume of sphere is 4/3 pi r cubed. There's only two variables. One is the radius, independent variable, and then v, which is the dependent variable. But we need to take the derivative with respect to the time implicitly. So let's find out. So dv over dt, because that would be the derivative with respect to the time of the volume. So the rate of change of the volume of a sphere. And then 4/3 pi, that's just the coefficient. We bring it down. And then using the power rule, we do have 3r squared. But don't forget one thing. R is the variable. So we need to take the derivative of that implicitly. So dr over dt. So again, the rate of change of the radius is 4 millimeter per second. And we want to find out the rate of change of the volume when the diameter is 100 millimeter. Again, this one is just mentioning about the diameter. So that means the radius, it's half of the diameter. So it's 100 over 2, which is 50 millimeter. And then basically we just plug in a number. So 4/3 pi times 3. Well, the 3 and the 3 can cross cancel. So the 3 and the 3 cross cancel. And then radius, so the one we have is 50. Quantity square. And then dr over dt, it's 4 millimeter per second. So basically just multiply those numbers. And let's see what I find out for this one on the calculator. So we got 4 times 4, which is what? 16. 16 times 50 square. So that's a big number. It's 40,000 times pi. So it's 40,000 pi. So eventually it's 40,000 pi. And the unit for this one, it's a cubic millimeter per second. Again, this one is about the rate of change of the volume and showing how fast the volume has been growing. So it's 40,000 pi. We don't round things off here. It doesn't say so. So we'll just keep it like that. So 40,000 pi cubic millimeter per second. Okay. So now the next problem is quite similar. So if a snowball melts so that its surface area decreases at the rate of 1 square centimeter per minute, and find the rate at which the diameter decreases when the diameter is 20 centimeter. Now this one is asking about the rate of change of the diameter. So one thing that we notice, so the surface area of a sphere, it's considered 4 pi r squared. And the interesting fact is that the derivative of this, which is the surface area, if you start with the volume of a sphere, take the derivative with respect to r, you'll get 4 pi r. So we're going to be using this formula to find out the rate of change of the diameter. And for those of you that might be wondering, there's no diameter here. But one thing that we can do, we can always set up the auxiliary equation. So one thing we notice, radius is considered d over 2. So instead of using radius for the surface area, so we want to rewrite the surface area in terms of the diameter. So then that would be considered 4 pi times d over 2 quantity square. Again, radius, it's d over 2. So what I'm doing here, I just replace that radius by d over 2. So we got 4 pi, so d squared over 4. So in other words, that means this one can be written as pi d squared, and that's the surface area of a sphere. So now from here we want to take the derivative. So the rate of change of the surface area, then that would be dA over dt. And then derivative of pi d squared. So we do have 2 pi times d. And don't forget, take the derivative of the diameter implicitly. So it's dd over dt. So make sure that you take the derivative of the variable with respect to the time. So 1 square centimeter per minute. So this one, that just tells you the rate of change of the surface area. So basically we just plug in a number. So 1. So that equals 2 pi times the diameter. So the diameter is 20 centimeter times 20. And then we want to find out the rate of change of the diameter. So we have solving for dd over dt. So 2 pi times 20, then that will give you 40 pi. Okay, so from here, dd over dt. So you divide it by 40 pi on both sides. So that means eventually dd over dt. So that equals 1 over 40 pi. And the unit for this one, guess what that is for the unit? Diameter is one dimensional, so just consider centimeter per minute. Okay? So 1 over 40 pi. Okay, so now let's find out another example in just a second. Okay, for the next slide. Okay, let's see what I got for the next one. So here's example 4 and 5. So 2 cars start moving from the same positions. One travels south at 60 miles per hour. Okay, 60 miles per hour for the first car. So that's just the velocity. Okay, so let's see. Yeah, the computer's a little bit slow here. So let's see, right? The eraser. So this one, it just shows the velocity of the first car. So 60 miles per hour. And then the other travels west at 25 miles per hour. Now make sure that you need to highlight the direction as well. So one is south. And the other one it's west. And the other car is driving at 25 miles per hour. Okay, so 25 miles per hour. And then at what rate is the distance between these two cars increasing? 3 hours later. So now let's just draw the diagram first. So one is going down south. Okay, so one is going down south. So that means the first car is going down south like this. Okay, so the other one is traveling west. Okay, so I need more space, so let me start it over with this one. So first car going south, and the other car is going west. Okay, let's use the other direction. Okay, like that. And then eventually you want to find out the distance that has been changed for the distance between those two cars. So the distance, eventually we want to find out the distance here. So one thing that we notice, one is going down south at 60 miles per hour. Okay, so 60 miles per hour. mph. And the other one is traveling to west at 25 miles per hour. It's a little bit slow. And then we want to find out the distance, the rate of change of the distance right between these two cars. So let's say that's dl over dt. And let's say this distance here is L. And the time is after 25, well, let's see. What's the time here? 3 hours later. Okay, so 3 hours later, so that's the time. Okay, so let me set up the new slide for this so we have more space to show work. Okay, so once again, so one is going down south, and the other one is going to west. And we want to find out the distance, the rate of change of the distance right between these two cars. Okay, the distance right between. Okay, so one is 60 miles per hour. And the other one, it's 25 mph. So first thing that you want to do, you want to find the distance of the car that's traveling. So the first car going down south after 3 hours later. So we do know that the distance is always velocity times the time. So 60 times 3, then you get 180 miles. And then another distance, okay, let's say D1, D2. So then that'll be 25 times 3, then that'll be 75 miles per hour. And then with the information that's given here, we can find the distance in between those two cars. Because this one is the right triangle, so we can use the Pythagorean Theorem. Okay, so using the Pythagorean Theorem to find L. So let's say this one it's x. Here's y. So we do know that x squared plus y squared equals L squared. So x squared, we do have 75 squared. Y squared, we do have 180 quantity square. And then L squared. So take the square root of the sum of the quantity square. Okay, so let's see what I got here. So 75 quantity square plus 180 quantity square. And then square root of the whole number. 38025. So I got 195. So that's the distance. But the thing is that we need to find out the rate of change of the distance in between these two cars. So again, we're going to use the Pythagorean Theorem one more time. This time we're going to use that for the derivative. To find the derivative. So derivative of x squared, 2x. Again, we want to take the derivative of the equation implicitly. So dx times dx over dt. And then y squared, derivative of y squared would be 2y. And then dy over dt. And then derivative of L squared, 2L. And then dl over dt. And now we just plug in a number. And so we can find out dl over dt. So 2x. So 2x, then that would be considered 2 times 75. Dx over dt. So dx over dt, which is 25. So 25. So a lot of number that we need to multiply here. And then 2 times y. Another thing that we can do, the 2 actually got cancelled because that's the greatest common factor. So the 2, there's no need to worry about the 2. So this one is just y times dy over dt. So we do have 60 miles per hour, which is dy over dt times y. And y we have, it's 180. So we can just swap those two numbers. And then over here we do have L times dl over dt. So L, we do have 195. And then solve for dl over dt. Okay, so let's just multiply those numbers and see what happened. So 75 times 25. So that would give you 1,875. And then plus 60 times 180. So then that'll give you 10,800. Okay, so over here, 195 dl over dt. Well, the rest of this, just solve for dl over dt. So combine these two numbers together and then divide it by 195. So let's see what I found here. So 10,800 plus 1,875. And then divide that by 195. So for dl over dt, I do have 65 mile per hour. Okay, so related rate problem. Okay, so now let's see what else that we have for the rest of this. So back to the slide. Okay, so here's another one. A water drought is 10 meters long and cross-section has the shape of the isosceles trapezoid. And that's 30 centimeter wide at the bottom and 80 centimeter wide at the top. And has height 50 centimeter. If the drought is being... Okay, so that's going to be the continuation. So if the drought is being filled with water at the rate of 0.3 cubic meter per minute, how fast is the water level rising when the water is 50 centimeter deep? That's a lot of information here. So one thing that we need to go back, first thing that you want to do, it's about the annotation. So we do know that the drought is 10 meters long. Okay, so the length or the distance. And we do know that the cross section, it's a trapezoid. It's isosceles trapezoid. Okay, so let's draw the diagram here. If that's isosceles trapezoid, it looks like this. Okay. And try to connect this, the bottom part, and then the top, then the bottom. Okay, so that's the water drought. And the cross section right here. So we do know that's isosceles trapezoid. That means there's two sides got to be congruent. Congruent, that means they're equal, same shape, same distance. So 10 meter long, so that means L is 10 meters. Okay, so now let's see what else that we have right here. And 30 centimeter wide at the bottom. So this distance right here, it's 30 centimeter. If you try to convert that to meter, that's about 0.3, that's exactly 0.3 meter. And 80 centimeters wide, so that means it's 0.8 meters wide on top. And that has the height of 50 centimeters, so that means the height here, it's 0.5 meter. Okay. So now let's see what else that we have. If the drought is being filled with water at the rate of 0.3 cubic meter per minute, so this one right here, guess what that tells you? So it's dV over dt. The rate of change of the volume of the water inside the water drought. And then how fast is the water level rising when the water is 50 centimeters deep? So eventually, what happened with the height? It's 0.5 meter. Now, you guys see that? What I did here, I convert all the unit from centimeter to meter. So I'm not going to cause any kind of confusion because that the rate of change for the volume for the water, it's also in terms of meter, cubic meter per minute. Okay, so now with all the information that we find out, so how do you guys find the volume for the trapezoidal prism? Because according to the shape, it's just like a trapezoidal prism. So one thing that we know, the way to find the volume of a prism, it's always the area of the base times the height. Well, the height of the prism, which is here, is L. So the way to find the area of the base here, we do know that's an isosceles trapezoid. So the way to find out the area, it's 1/2 times the upper base plus the lower base times the height. Okay, so that just takes care of the area of the base of the trapezoid. And then L, which is the length of the water drought, which is 10 meters. Okay, so now we're going to use all this information to find out exactly what to do on the new slide here. So let me just trace all the information that I have, and then I'll just transfer that to the next page. So we do have volume 1/2 B1 plus B2 times the height times L. And we do know L is 10 meters long. And then B1, upper base, which is 0.8 meters. Lower base, 0.3 meters. And the height of the water drown is 0.5 meters. And according to the next slide, let's see what else now we have. dV over dt. So that's 0.3 cubic meter per minute. And then we need to find out the rate of change of the water, the height of the water when the water is 50 centimeters deep. Okay, so let's find out. Okay, on the new slide here. Okay, so once again, so let me just redraw that water drown. So trapezoid, and then we just want to extend this one, and then the bottom, then the top, then the base. Okay, so one thing that we notice, so here's the water level, so filled with water. So the height, it's only 0.5 meters deep. Again, the length for this one, so the length for this one, it's 10 meters. Okay, again, so the formula that we have, it's 1/2 times B1 plus B2 times the height. Well, gotta be careful with the height right here. The height here, that's just considered a variable. And then L, that's just a constant. So let's just plug in a number. So we have 1/2. So B1 plus B2. So B1, which is 0.8. And B2, which is 0.3. And then the height, it's a variable. And then the length, which is 10 meters. So from here, we can just simplify the equation a little bit. So 1/2 times 10, we got 5. 0.8 plus 0.3, we do have 1.1. So times the height. Well, this one is not the area, it's actually the volume. Excuse me, so let me fix that. So it's the volume of the water drown. Okay, so that one right there, so that's the volume. It's all volume. So once you try to simplify it, so it's 5.5 times the height. So for those you might be wondering, what about the rest of the element? Anything that's considered variable? Well, again, the depth, the only thing that is considered a variable is just the depth of the water. Everything else, they're just constant. They never change. So that's why it's just like plugging a number here. So now let's find out what the derivative is. So we got dV over dt. And then 5.5 times the derivative of h, which is what? dH over dt. Okay, so another thing that we noticed, the rate of change of the volume for the water level, it's 0.3 cubic meter per minute. So plug in a number, 0.3, 5.5. dH over dt. So now you want to find out how fast the water level is rising. So that means you want to find out the rate of change of the height of the water level. So divide both sides by 5.5. Okay, so let's see what that is. Or the other way you can do it is just like converting it to fractions. So it's just like 3 over 55. Because you don't want to round it. So 3 over 55, that's a very small number. So then that's dH over dt. And the unit for this one is meter per minute. Okay, so let's see what that is. 3 over 55. So that's about 0.054. Repeating. So 0.054 with 54 repeating. Okay. So now let's go back. The last problem we have. Well, actually for this slide, we do have, yeah, this one is the last one. We're not going to do the tracking problem. If you see anything like this on the homework problem, just erase that. Just forget it. Don't worry about it. Okay? So we'll just do the example 6 for the last one today. So a television camera is positioned 5,000 feet from the base of the rocket launching pad. Okay? So that means the diagram is going to be like this. So here's the pad. Okay, so here's the camera. Well, the pad is actually over here. So the camera is also over here. So this one is the base of the rocket. You can say that's the base of the rocket. Okay, so it's flying this way. So again, this one is a right triangle. And the angles of elevation, so the camera, angles of elevation, let's say that's theta, has to change at the correct rate in order to keep the rocket inside. Well, because this one it's, constantly, shifting up. So that's why the angles be moving up and down. Okay, so it's keep rising up like that. So it's going this way. So let's find out what that is. So the rocket rises vertically and its speed is 700 feet per second. So this one, you can say that's dH over dt. So 700 feet per second. Okay, so now let's see what else that we have for the rest of this. So 700 feet per second when it has risen 4,000 feet. Okay, 4,000 feet, then that would be the height. And how fast is the distance from the television camera to the rocket changing at that moment? Okay, so first part of the question here. So we need to find out that the rate of change of the distance. dl over dt. And then the second part of the question here. So if the television camera is always kept aimed at the rocket, how fast is the camera's angles of elevation changing at that same moment? So that means we need to find out d theta over dt here. So this one dl over dt. Okay, so now let's go back to the diagram here. So in order to find out dl over dt, we do know the angle. So one thing that we can do is about using the, either the Pythagorean Theorem or using SOHCAHTOA. Okay, so 5,000 feet, I didn't label it. This one is the distance from the distance between the camera and the base of the rocket ship. Okay, so now let's just set up the equation for the first part. So let me just do it right here. Okay, so for the first part, we do have 5,000 quantity square. Again, using the Pythagorean theorem. So plus h squared, so that equals L squared. So L, which is the distance from the camera to the tip of the rocket ship. Okay, so here's the distance, L. So we can say that it's L right there. So we do know that dH over dt is 700 feet per second. So this one is always constant because that's always keeping the same distance. Okay, so now let's set up the derivative. So derivative of 5,000 squared, then that'd be 0. Derivative of h squared, then that'd be 2h times dH over dt. And then L squared, that's just like 2L. But don't forget dl over dt. That's what we need to find out. Okay? So everything else, just plug in a number. And now for those you might be wondering, how do you solve for L? Well, L, we can use the Pythagorean theorem. So it's 5,000 square plus 4,000 because that's the height of the rocket ship. So after it has risen 4,000 feet. So once you solve for L, and then you just plug in a number. Again, H is already given. Okay, so let me just plug in the charger. It's almost out of battery here. Okay, so now let's see what else that we have for the rest of this. So once you solve for L, just plug in a number, plug in H, plug in dH over dt, and then you solve for dL over dt. So now, this one can figure out what to do. And then what about for part B? So for part B, okay, this one, deal with that later. Okay, so for part B, so let's see what I can do. Back to the diagram. So this one, we do know that it's a constant base here. And this one, the height, it's a variable. So we can use SOHCAHTOA to figure out d theta over dt. So let's use tangent of theta. So for part B, you want to find out the rate of change of the angle. So tangent of theta. So then that would be considered h over 5,000. Okay, so derivative of tangent theta, then that would be considered secant square of theta. And then d theta over dt. Again, implicit derivative. And then derivative of this would be considered dh over dt times 1 over 5,000. And then basically just plug in a number. Okay, again, once you plug in a number, and then you can solve for d theta over dt. And for those you might be wondering, how do I solve for theta? Well, the way to solve for theta, all you need to do is just take like inverse of tangent of h over 5,000. Well, again, h, the height of the rocket ship, is 4,000. So 4,000 over 5,000, which is what, 4/5. So once you get that angle theta, so all you need to do is just plug in a number. And then once you solve for theta, plug in dh over dt, plug in that, the rest of the element, and then just solve for d theta over dt. Okay, so again, any questions that you have, just put into the comment on the YouTube channel. Okay, so we'll take a look at that. Any other problem, any concern that you have later on. Again, that's 700 feet per second. That one's considered dH over dt. Okay, so try to finish the last problem and then get started with the homework over the weekend. Okay, so see you guys later.